All right, revisiting compound interest. So we know if we're given some interest rates, then sometimes we need to cut it up depending on how much time has gone by. So I'm going to introduce a new variable, n here, where n is the number of times per year that we get interest. So we're going to call that compoundings per year. And so when we take our interest rate and divide by the number of compoundings per year, we could call that our periodic interest rate. And if we take some initial amount, let's call that P, then we also know that if we multiply by 1 plus that periodic rate, which is now called R over N, we can get a quicker new amount. And let's call that F for future value. Call it A for amount before. And then we just keep increasing the power for how many times how much time went by. And there's two ways to think about that. If N was equal to months, then there would be 12 times per year. If N were related to days, then we'd have 365 times per year. So that would be days per year. So if, say, 10 years went by, well, it would be 10 times 12 or 120 periods. If 10 years went by for daily, it would be 10 times 365 or 3,650. Either way, that power here is the number of years that have gone by. Usually we call that T times the number of compounding periods per year there are. So this is a new formula for compound interest that we can apply. And it turns out this idea of adding on to 100% for a rate can be used in a lot of situations, not just compound interest. And it also goes backwards too. If we have a situation where we're regularly losing the same percentage, we could apply it there too. That's what I want to look at next. So we're going to take a look at car depreciation. So suppose there's a new car and it's $24,000. And let's say this car depreciates or loses its value at a rate of 12% each year. So after 1 year, what's going to happen is I'm going to have less. The car's going to be worth less than it was. So if I take 12% of 24,000 and I calculate that amount, so let's whip out a calculator. So let's go over here. 12% times our $24,000 car, we lose $2,880. And so after 1 year, that $24,000 drops by $2,880 and now is only worth $21,120. And we actually know a shortcut for that process. Instead of doing this long way, $2,880 that we lose, and then taking the $24,000 and subtracting that $2,880 and getting that, what was it, 21,000. Let's see, where we're going to go. 21,200, 120. Oops. Where's it go? 21,120. We can do it a little quicker. So all of this information can be combined by saying, well, we started off with $24,000 and that was 100% of what we started with, but now we're losing 12%. And if we lose 12%, that means the car retains 88% of its value as a decimal 0.88. So now I should have 24,000 times 88%. So let's ask our calculator what it thinks. And let's put that over here. Let's put it here. 1 year again equals that 24,000 times 88%. And there's that same $21,120. And if that repeats over time, we're just going to keep multiplying by that 88%. And so we can develop a model for over time, the value of the car, let's call it V for value, is going to be the initial value, 24,000, times the amount we keep, which is 88%, because we lost 12%, raised to the power t, which is however much time in years goes by. So then we could say, what's the value in 10 years? So 10 years later, my pen is locking up. I'm pushing the wrong button. 10 years later, I should have 24,000 times 88% to the power 10, which I bet isn't going to be all that much. So let's jump to 10 years later. So we have our initial 24,000 times 0.88 to the power 10. Not too bad. $6,684.02 would be the rough value of that car. This is percent depreciation. There could be linear depreciation where we just assume the car loses about $3,000 per year and we just deduct $3,000 over time, which is a slightly different way of looking at things. And that was talked about in the previous course. If you didn't take the previous course, you looked at it a different way, well, we're going to check out some other models for this. So let's check out caffeine here next. So a typical cup of coffee has about 100 milligrams, an 8-ounce cup of coffee. And your body metabolizes that caffeine after drinking it. And let's just say an hour later, a person has 90 milligrams. And so the question is, how exactly is the body metabolizing that? What does it look like over time? So if we take a look at hours versus caffeine. Come on, pen, you can do it. Let's call it 0 hours when we consume the coffee. We have 100 milligrams in our system. And then 1 hour later, we have about 90 milligrams in the system. And so to get from here to here, there's a couple of ways I could think about it. I could look at it in terms of the absolute change. Which would just be 100 minus 90, which is 10. And so then 2 hours later, I would have 80 milligrams. 3 hours would be 70, right? Keep dropping by 10, all the way down to 5. And let's look to 6 hours later, 40 milligrams in the system. That's one way of looking at it. Another way of looking at it instead of absolute change is relative change. Relative change is also called percent change. So percent change, we take that absolute change, the amount of change, and compare it to what we started with. So the relative change would be a drop of 10 out of 100, and that would give me negative 10% or negative 0.1. So that's a different model for the caffeine. If we lose 10%, what do we keep? Well, we would keep 90%, right? So a model for that would be to take that 100 and multiply it by 0.9, and that's going to give me 90 milligrams after an hour. After 2 hours, I would take the 90 times 0.9, and that would give me 81 milligrams. And I can't easily do it in my head after that, but you get the idea. It's going to drop down. So let's compare these two changes in our spreadsheet and then figure out which one is right. So let's see. We have caffeine, and we'll call this one ABSCH for absolute change, and then we'll also do caffeine relative change. Percent change. Not percent, percent. There we go. So either way, we start off with 100. The way above here, we just lose 10 each time. So we take the amount above minus 10, and we fill down just that formula for 6 hours. That gives us the 40 we predicted before. Other method is to say drop by 10, which means we retain 90%, and drop that down and see what we get. So we get a slight difference here. We get, with the absolute change, we'd have 40 milligrams after 6 hours. With the relative change, we'd have about 53 milligrams. Which one is the better model? Well, the general theory about this is that caffeine has what's called a half-life. Let's fill this down a little bit. Dot, dot, dot. And so relative change over here was about 53 milligrams. So caffeine, half-life. Six hours. What does that mean? So if you look it up, you'll get some information on this, and it's somewhere 5-6 hours. So that means after 6 hours, so if we were considering my table where you had hours versus caffeine, 0 hours we had 100 milligrams. 6 hours later we would end up with 50 milligrams. And another 6 hours after that, so 12 hours later, there would only be 25 milligrams in the system. Okay, so 100 milligrams is noticeable, 25 milligrams may not be noticeable to most people in their system. So the question is this relative change or is it absolute change? Well, if you look at the change in this 6 hour span, right, so I went up 6 hours here, I went down 50 milligrams there, I went up 6 hours here, but I only went down 25 there. So this is not linear. These do not line up. Therefore, this is not absolute change. We're not changing by the same absolute amount each time. So this is a relative or a percent change. So, how can we play with that? Well, the formula we could develop here is that given so we're trying to calculate caffeine, we started with 100 milligrams, and then we have this constant multiple. Now, I estimated it at 0.9 before. It's not quite that if I go with the 6 hours. So we're just going to compare the 6 hours. What happens is I get to cut that 100 in half every time 6 hours goes by. So if you give me a time and the number of hours, I'm just going to divide that by 6 because I'm looking for groups of 6. Okay, so here's one group of 6 right there. And then over here, I have two groups of 6. And if 18 hours went by, that would be half again, so 12.5 milligrams. That'd be another group of 6. So this would be the third group of 6. And so 18 divided by 6 is 3. And so let's just confirm this formula works. For caffeine, slightly different version than I have here. That, come on, go away. There we go. Let's see, I wanted to go down to 18 hours later, which is off my chart. 100 milligrams times 1/2 raised to the power, and I thought the power should be 3 because 3 groups of 6 went by. And yep, there's my 12.5 milligrams of caffeine. So cleaning this up a little bit more to kind of apply it to the other problem we looked at. If I pull out the time here, oh, my pen is going crazy. Come on. No. Uh-oh, my computer is struggling to live right now. Hello? What's wrong with you? Oh, it's user error. Huh. Apparently this pen has magic buttons that I'm not used to yet. Sorry, I have a new pen and whiteboard. All right, let's see, cleaning up that formula. So if I pull the t out, then I have 1/2 to the power 1/6. Right? I'm pulling the t out here. And is this legal? Let's just double check. I'm going to throw an extra parentheses around here because I'm pulling that t out. if you take a power to a power here, you multiply them. 1/6 times t is t over 6. So that's okay. So I want to analyze what my new base is here. So the 100 is my initial amount here. My base is this blue part right here. So what is 1/2 to the power 1/6? That's my new base. So over here, for the base amount, I've got equals, and I need parentheses to do this right, 1/2 raised to the power parentheses 1/6. I get a base of about 0.89-ish, so almost 90%. And if you think that 100% is what we started with, what we had in the previous period, that means the rate of decrease here would be 1 minus that, or about 11% if we rounded that to the nearest hundredth. Okay. So I was guessing at a 10% decrease in caffeine, or 10 milligrams from 100, and if the half-life of 6 hours is correct, it's actually about an 11% drop each time. So if we go with the 11% drop each time, so we start with 100 times, we keep 89%, oops, way, 89, there we go, raised to the power how many hours went by, which is over here in this column. I can recalculate and say that in 18 hours there'll be about 12.25 milligrams of caffeine. And these decimals are probably not going to be very accurate because this is just an estimation, so whole numbers of caffeine is probably better here. So notice the percent decrease is different than the linear decrease. There's a curve going on to it. So I'm going to eliminate this column just to take a quick look at the graph. Where's delete column? That was it. Delete column. Thank you. All right, so I'm going to skip the 18, just do up through 6. Insert chart. Zoom out. Yeah, notice it looks kind of like a straight line, but if we went out a little farther, it won't. So let's go out a little farther. I guess we could included the 18 in there, but let's fill in some gaps. So let's do after 6, we could do 12 and then 18. I think we'll get a better shot of what's going on, the curve that's happening. Yeah, so here you can see a little more of the curve. It is not a straight line from end to end. The caffeine kind of drops down, steeper at first, and then it kind of slows down the rate at which we get rid of it after that. So these kinds of problems are exponential growth and decay problems. Last bit of information for now. Exponential change. And so Y, our output here, could be caffeine, could be the price of a car, could be the amount of money in an account, is equal to some starting amount, and that goes by different letters, some base amount, and then the amount of time that goes by. The base amount can be found a lot of ways. One way we saw earlier for that base amount was we had 100% plus some rate. And that rate could be positive or negative. It could be increasing or decreasing. So we could have a growth situation, like interest in an account, where R might be something like 2%, some positive number. On the other hand, we could have a decay situation, like a car depreciating in value. And in that case, the interest rate might be a little bit different. We might have R is a negative amount. So negative, dropping by, say, 15% or 12% or 10% or 11%. So we can go up or down. So the base that we have, that A, different situations will arise. If it is a increase, then the kind of graph that we'll see if we plot those points, it'll curve upward on an increase. If it's a decrease, then what we'll usually see is that there's a drop downward. Okay, and it will curve. That's it for now. Stay in touch and do good math. See you in the future.